Have you ever looked at a number and just kind of assumed you knew what it meant? Well, what if I told you that numbers have a hidden language, a secret code that tells you just how precise they really are? Today, we're cracking that code. We're talking about significant figures.
All right, let's just dive right in with a little scenario. I want you to meet two students, Li Ting and Kumar. They've been given what seems like a super simple task, but it's going to reveal something huge.
So here we go. They're both measuring a volume of water. Li Ting takes a look at her measuring cylinder and says, yep, it's 13 cubic centimeters. Easy enough, but then Kumar, who's using a different cylinder, reports his measurement as 13.0 cubic centimeters.
Now wait a second, you're probably thinking, isn't 13 exactly the same as 13.0? I mean, mathematically, you're right, but in the world of science and measurement, there is a massive difference between those two numbers. So what on earth is the deal? The answer, in a single word, is precision. That little zero Kumar tacked on the end, that wasn't an accident. It tells us something incredibly important about his measurement. And the language we use to communicate that precision, that's what we call significant figures.
So to solve this little puzzle, we've got to learn the basic grammar of significant figures first. Don't worry, we're going to start with the easy, straightforward rules.
Rule number 1, and trust me, this is the easiest one. It's our foundation. Any digit that is not a 0, so, 1, 2, 3, all the way up to 9, is always, and I mean always, significant. It counts, period, no exceptions.
For example, let's look at the number 7,258. It's made of 4 digits, none of them are 0. So that means it has exactly 4 significant figures. Simple as that. The 7, the 2, the 5, and the 8, they all matter.
Okay, but what about zeros? Well, rule number 2 is for what I like to call the trapped zeros. Any zero that gets sandwiched between two non-zero digits is also significant. You can think of them as being locked in place. They can't get away.
Here's a perfect example. 302008. See that 0 between the 3 and the 2? It's trapped, so it counts. And what about the 2 zeros between the 2 and the 8? They're trapped too, so they all count. That gives us a grand total of 6 significant figures.
All right, we've got the simple ones down. Now let's get into the trickier rules for zeros. These are the ones that are finally going to help us solve the mystery of Li Ting and Kumar's measurements.
Rule number 3 is all about those leading zeros in a decimal. If you see a number like 0.057, those first zeros before the 5, they don't count. They're just placeholders. Their only job is to show us where the decimal point lives.
And now, the big one. Rule 4. This is the key to our entire puzzle. In any number that has a decimal point, the zeros that come at the very end, after all the other digits, are absolutely 100% significant. Why? Because they are there to show precision.
So, let's go back to Li Ting and Kumar. Li Ting's measurement, 13, has 2 significant figures. This tells us her measuring cylinder is probably marked for every whole number. But Kumar's 13.0, that has 3 significant figures. That trailing 0 is there on purpose. It means his tool is 10 times more precise. He was able to measure to the nearest tenth of a cubic centimeter. That's the real difference.
And this is the critical point. As our source material puts it so well, you can't just add a 0 for fun. That 0 in 13.0 is a deliberate statement about how good the measurement is. It is meaningful, and it is very, very important.
But what about when you see zeros at the end of a whole number without a decimal point? This is where things can get a little tricky and where context is literally everything.
Let's imagine the number 7,500. Bernard looks at it and says, that's 2 significant figures. But Siti says, nope, it's 3. And then Raju comes along and is certain it's 4. So who's right? Well, the crazy answer is, they all could be. And this table shows us why. It all comes down to how that number was made. If 7,500 was rounded to the nearest 100, Bernard's right. Only the 7 and 5 are significant. If it was rounded to the nearest 10, then Siti's got it right. And if it was an exact measurement right down to the ones place, then Raju takes the prize.
And this brings us to our 5th and final rule, I promise. Those zeros at the end of a whole number are just ambiguous. We can't know for sure if they're significant without more information about how the number was rounded or measured.
Okay, so we know how to read significant figures. Now let's flip it around and put this knowledge to work in a super practical way, rounding numbers to a specific level of precision.
Let's try to round 8,982 to 2 significant figures.
First, we count in 2 spots from the left, which lands us on the 9. That's our target. Next, we peek at its neighbor to the right, which is an 8. Since 8 is 5 or bigger, we have to round up, so the 89 becomes 90. And finally, we just fill in the rest with placeholder zeros to keep the value right, which gives us 9,000.
So, if there's one thing you take away from all this, let it be this. Significant figures are not just some boring, arbitrary rules from a textbook. They are a universal code. It's how scientists and engineers all over the world communicate how certain they are about a number. It's the language of confidence.
So, the next time you see a number out in the wild, on a food label, in a news report, anywhere, take a closer look. Now that you know the code, what hidden stories about precision are those numbers just waiting to tell you?